we are going to need to talk about just a couple of lasting concepts that are either kind of implied or that are derivatives of some of the calculations that we have done already. So one of those things, we've talked about how to determine pH and pOH from hydrogen and hydroxide concentration. What if we had to go the other way? Well, if we had to go the other way, what we would use is something called the anti-log. The anti-log is on your calculator the secondary function of the logarithm. It looks like a 10 to the x kind of symbol. And so all that you would need to do for these kinds of problems is if you were given the hydrogen concentration, or if you're given the pH, to find the hydrogen concentration, you just raise that pH 10 to the negative pH power. And if you have the pOH, to find the hydroxide concentration, you would take 10 to the negative pOH power. So for a question like this, what is the hydronium concentration in a soil sample where the pH is 6.20? Well, we're going to use this equation here, which means that the hydronium concentration is going to be equal to 10 to the negative 6.20. On your calculator, the way of going after that, again, I've got two different models of calculator here. I can show you on both. It's the same in either case. The opposite of the logarithm function is the anti-log function. So my pH was 6.20. I would put in 6.20, make that negative by pushing that plus minus button. And then I'd hit second log to access the anti-log. It would pump out a number, and on the TI here, unfortunately, they don't give us scientific notation already. Not without us changing the mode. 1, 2, 3, 4, 5, 6, 7. This would be 6.3 times 10 to the negative 7th as the molar concentration of the hydronium. Casio's, same thing, a little bit more straightforward just because it automatically converts into scientific notation for you. 6.20, turn that into a negative, and then it's shift log, and I get the same number, 6.3 times 10 to the negative 7th in either case there. Now, if you have a scientific calculator that is program oriented, Brianna, can I borrow yours for just a second? This one's a little bit different because instead of having to input the numbers first and then input the function, you kind of do it in reverse. You put in the function and then you put in the number that you're taking. So in this case, with this one, it would be second log. That would bring up the anti-log function, and then you'd type in negative 6.20. You'd still get the same 6.31 times 10 to the negative 7th. So either any way that you look at it, regardless of what your calculator looks like, that's how you're going to do it. And so, again, coming back to the problem at hand, ten to the negative 6.20 is 6.3 times 10 to the negative 7th molar, which would be the hydronium concentration for this particular sample. And so what we can see is that we've described basically 4 different ways of describing pH or concentration of a solution. There's the pH, there's the pOH, there's the hydronium concentration or the hydrogen concentration, and there's the hydroxide concentration. And all 4 of those units are interrelated with each other. We can see that hydronium and hydroxide are related to each other by that 1 times 10 to the negative 14th calculation. We can see that pH and pOH are linked together by the fact that the 2 will add together to give us 14. And we can see that we can interconvert between hydronium and pH either by taking the logarithm of the hydronium or the antilog of the pH to find whatever's missing. And if we can do it to the hydronium side, we can certainly do it to the hydroxide side as well. So any conversion that we want to make within these 4 parameters, we can make. So if I want to turn a pH into a hydroxide concentration, I can do it by first figuring out the pOH and then figuring out the hydroxide concentration. Or I can find the hydronium concentration and then turn it into a hydroxide concentration. I can connect any of the diagonal lines by going around the square. And this is a really important thing for us to recognize, because what this means is that we can literally calculate anything about a solution if we know its pH or its pOH, if we know its hydronium concentration or its hydroxide. All I need to know is one of those things, and I can figure out the other 3. All right, let me stop here just for a second and if you have any questions, let's kind of draw them out now. Okay, Brianna? You would be given all of these equations, okay? So the point isn't to memorize them, it's to know how to use them. All right, let's do an example. When the pH of water in a lake falls below 4.5, the lake may be considered dead because few organisms could actually survive that harsh of an acidic environment. What is the pH of a lake that has a concentration of hydroxide of 3.2 times 10 to the negative 9th molar? Could we consider this lake dead? So if we hop back just for a second to our square diagram here, what we will see is we have this concentration. What we need to figure out is the pH. Now, to go across the diagonal, I need to go around the square. Now, there are two directions I could go. I could go from hydroxide to hydronium, hydronium to pH. Or I can go from pH to pOH, or I'm sorry, hydroxide to pOH to pH. And that's actually the method I would prefer to do, because in this one we've got a logarithm and a subtraction as opposed to a division and a logarithm. And I just find that addition is way easier than division. So that's the process that we are going to use. Now we need to go about the execution of it. So if my hydroxide concentration is 3.2 times 10 to the negative 9th molar, remember that pOH is equal to the negative log of that concentration. So the negative log of 3.2 times 10 to the negative 9th. So into my calculator I go, 3.2 times 10 to the negative 9th. I hit the log of that. The log of 3.2 times 10 to the negative 9th is negative 8.49. The opposite of a negative is a positive, so my pOH is 8.49. Remember that pH plus pOH have to equal 14. So if my pOH is 8.49, pH is going to be 14 minus 8.49, which would be 5.51. So pH for this lake is 5.51. Is this lake dead? No. pH needs to be below 4.5. It's above. So no, we would not consider this lake dead. With its high pH, we would be potentially concerned about it, but we would not consider it dead. Right. Any questions with this example? Yes. So the pOH would be positive 8.49. When I do the logarithm, it gives me a negative 8.49. Remember that pOH is the opposite of that logarithm. So the negative of negative 8.49 would be the positive 8.49. So ordinarily speaking, your pH and your pOH values should come out to be positive values. The only times that they don't is if you have something that is really highly concentrated. Talking about a concentration greater than 1.0 molar. If the concentration is less than 1.0 molar, the numbers are going to be positive for pH and for pOH. Other questions? All right, so how do we go about measuring pH? Well, there are a number of different ways that we can do it. Those of you that own a pool or a hot tub or have had to do any kind of water testing at home, like in a jacuzzi or something like that, you're probably familiar, at least in some part, with these kinds of local at-home test kits. How these work is the paper or the solution, you put an indicator into it, the indicator changes color based upon the pH of the water or based upon the concentration of chlorine or bromine or whatever in the water. So that's one method. Indicators are a very quick and easy way of determining pH. When we need to be a little bit more precise, a little bit more accurate, we'll turn to something like this. This is an ancient model. This is probably a good 20, 30 years old, but this is what a pH meter looks like. Nowadays, they're a little bit more sophisticated. They're a lot smaller. But pH meters work on the premise of different electrical impulses being generated by different pH solutions. And so the electrode here measures the electrical impulse, and based upon its calibration, spits out a pH value for the solution. The difference between them, this one is considerably slower and bulkier. It's a lot more finicky, but it gives us much more accurate, much more precise results. If we need that level of accuracy and precision, we have to go to this method. If we're looking for general kinds of ideas about pH, these indicators strips tend to be the best way to go. And you saw this in lab, those pH hydron strips. They're not terribly accurate, but they give you an idea. Okay, this one turns red, it's acidic. This one turns blue, it's basic. This one's kind of greenish, it's kind of in the middle. Indicators generally are brightly colored dyes that have acidic basic properties associated with them. So phenolphthalein, which is an indicator that you've used a lot in the last 3 weeks. This is the molecular structure of phenolphthalein. Now, what happens is that when phenolphthalein encounters a base, that base is going to break this bond that makes that 5-membered ring right there and form a new substance. The new substance here, because of that lack of bond, now picks up a good bit of color. It turns pink as a result. Whether or not we've got enough enough base present to actually break that bond to form the colored version of this dye is the whole point of phenolphthalein. Phenolphthalein can do this somewhere between pH 8 and 10. So once we hit pH 8, 9, 10, we start to see this transition taking place, where that bond breaks and we go from a colorless dye to a pink dye. But phenolphthalein is not the only indicator that exists. We also have indicators that can go over a wide spectrum of colors and pH ranges. So here's our phenolphthalein. Again, this is the one we're familiar with. And we see that its color transition is right in that 8 to 10 range that I described. Again, I did a horrible job of drawing straight lines there, but you can kind of see that between those two pH values, that's where the first transition of that color takes place. But we can see that there are a number of different dyes that will change colors at different ranges. This one in particular here, thymol blue, we actually see it has two different color transitions that take place. Somewhere between 1 and 3, it'll go from a red color to a yellow color. And it'll stay yellow from about pH 2.5 to pH 8. And then somewhere between 8 and 9.5, it'll change colors again and go from yellow to blue. So there are lots of different indicator colors and indicators that exist. Those of you that have dealt with pools or hot tubs before, the dye that is in a lot of those at-home test kits is something called methyl red. And what methyl red really is testing for, we can see that if your water is particularly acidic, methyl red will pick it up. There's another one, phenol red, that's looking more in the proper range of where we would like our water to be. And so if it goes below pH 6.5, we start to see it yellowing. If we see it in the red region, we know that's at pH 8.5 or above. And generally speaking, we want our water to be somewhere in the middle there. So we're hoping that it actually appears kind of orangish when we test it. Because that means that we've got a mixture of the yellow dye and the red dye. And so it's going to kind of appear orangish in that scenario. Now you can actually make your own acid-base indicator at home, and it's none of these. Red cabbage juice. If you take a red cabbage and basically boil the heck out of it, filter off the results, the resulting juice will be this kind of reddish color that will actually change different colors based upon the pH of the water that it's in. Red cabbage juice is actually the basis for something we call universal indicator, where we can see that at neutral pHs, this substance kind of takes on a purplish pink kind of color. As it gets more acidic, it becomes more red. As it gets more basic, it becomes more blue and then green and then actually yellow. Again, this is something you can make at home. Doesn't take very long to do. It's kind of a cool experiment to do at home, especially if you have kids or younger siblings, things that you're trying to kind of impress them with. You can take half an hour, make this stuff up, and then just start exposing it to like lemon juice, vinegar, household bleach, those kinds of things. Obviously don't let them drink it, but you can see these color transitions that are taking place just with normal household items. It's kind of a cool experiment to do. So with that, we will end our study here of chapter 13, talking about acids. But again, I just wanted to kind of tie up some loose ends with this chapter. Not stuff that you necessarily would have saw in the post-lecture over the weekend, but some interesting and useful kinds of information. Any questions before we put this one away? All right, so what we want to do then is our primary topic for this week comes out of chapter 12. And in chapter 12, we are going to look at reaction rates and a phenomenon known as chemical equilibrium. Now, chemical equilibrium is something that we've already alluded to and talked about a little bit in previous chapters. In particular, in chapter 13, we talked about weak acids and weak bases and reversible reactions. Well, chemical equilibrium is a name for the study of those reversible reactions. So out of this chapter, you can see there's a good bit that is in here, and a good chunk of it we are not going to talk about at all. Sections 4 and 5 in particular talk a whole lot about like calculating equilibrium constants and determining extents of reaction. And honestly, I do that stuff with my general chemistry 2 students, and that's really a topic of conversation for them. We're going to focus on conceptual kinds of things that don't require us to break out our calculator very often. But still, we can kind of wrap our brains around the whys for some of these things happening. So we're going to start by talking about reaction rates. When we talk about rates of reaction, what we're really getting into is measuring how fast or how slow a chemical reaction proceeds. And we know just from experience that some reactions are going to be naturally faster than others. For example, if you strike a match and the match catches on fire, that reaction is going to be very fast. Within a matter of seconds, all of the consumable material on that match is going to be burned out, and the reaction will be over just that quickly. That's a fast reaction. And it's naturally fast because of the nature of the reactants involved. Other reactions are naturally slow. If you leave your car out in the field, it doesn't turn into rust overnight. But over the course of weeks and months, eventually the metallic parts of the car are going to start to corrode and decay. It's a process that occurs naturally, but does not necessarily occur quickly. And so that's the thing that we have to kind of separate from ourselves in our minds. Just because a reaction is slow doesn't necessarily mean that it's not going to happen on its own. And just because a reaction happens on its own doesn't necessarily mean it's going to happen quickly. There's a difference between whether a reaction is going to occur. We call that field in chemistry thermodynamics. And how quickly the reaction occurs. We call that field kinetics. The two fields are separate from each other. And we need to point that out before we kind of move forward. Now, when it comes to reaction rates, there are some things that we can look for that will help us to determine whether or not a reaction will occur quickly or slowly. Or if we're looking at it from a standpoint of speed, there are some things that we can do to a reaction to manipulate it to help it to go faster. So in particular, we can look at 4 different areas where improving each of those areas could help us to improve the speed of a reaction. The first of those areas is temperature. In temperature, we're looking specifically at higher temperatures. We know that when temperature increases, we see an increase in the kinetic energy of those molecules inside of the reaction, and that generally leads to faster chemical reactions because the molecules themselves are more energetic. We can also look at things like reactant concentration. In reactant concentration, we can recognize that generally speaking, increasing the concentration of our reactant does tend to increase the rate of reaction. The more stuff I have, the easier it is to get it to react. In a similar kind of way, we can talk about surface area. With surface area, Again, we're looking at how much available surface is present and available to react. The more available surface for reaction, the faster the reaction is going to go. We can look at it kind of this way. If I was going to try to light this roll of paper towels on fire, what would be faster? Me holding up a match to the bottom of this roll, or me spreading out all of these paper towels and lighting all of them all at the same time? It would obviously be the second scenario. When the paper towels are rolled up like this, there's only a minimal amount of surface area of the paper that's actually exposed to the oxygen in the air to allow the reaction to occur. But if I spread it out, now all of this is exposed to the oxygen in the air. They're all going to be capable of reacting all at the same time. Whereas anything that is still in the roll, I can only access what is on the outside. That's going to make the reaction a heck of a lot slower. Finally, we can look at catalysts. Catalysts are things that will increase the reaction rate itself, but they themselves do not actually participate in the reaction. So catalysts never are used up by a chemical reaction, but they generally help the reaction to take place more quickly. So let's take a look at some pictures to kind of help us to put these into context. So concentration. In my flask on the left, I have a 1 molar concentration of vinegar. In the flask on the right, I have a 3 molar concentration of vinegar. And inside both of these balloons, I've got what looks to be baking soda. And so we know that baking soda and vinegar will react to form carbon dioxide gas. But we can see that very clearly, the higher concentration of acid is causing a faster reaction to make more carbon dioxide more quickly than the 1 molar was. Now we can see that the 1 molar is reacting. We can see that that balloon is inflating, but to a much lesser degree, much slower. So again, generally speaking, increasing concentration does increase the rate of reaction. Makes the reaction go faster, makes the reaction react more vigorously. Let's look at surface area. Now, you did a form of this reaction in lab a couple of weeks ago. In the left-hand panel, we have an iron nail. Now, an iron nail has a relatively low surface area. Even though the surface area is kind of, spread out, we've got a lot of surface area on the surface of that nail. The interior of that nail is pretty much hidden. So when we heat up that nail and put it in oxygen, we'll see that the nail is going to glow as some of that oxygen and some of that iron interact with each other. But if I took a similar mass of steel wool and I separated the strands of the steel wool from each other and did the exact same thing, I would see that once I put it into that oxygen environment, a much more vigorous reaction is going to take place. These firework reactions or sparkler reactions are the direct result of the iron in the steel wool reacting with the oxygen. Now, nothing has changed between the two panels. We have the same ingredients, iron and oxygen. We have the same masses of each ingredient. The only thing that is different is that steel wool has separated those iron strands from each other, and we now have more surface area of iron with which to react. For catalysis, the reaction that we are viewing here is the reaction between hydrogen peroxide to form water and oxygen gas. Now, this reaction will occur on its own. If you buy a bottle of hydrogen peroxide, it is stored in a brown bottle. The purpose of the brown bottle is because light will cause this reaction to occur and the hydrogen peroxide to decompose naturally on its own. It's also why hydrogen peroxide has an expiration date. Because even if you keep it sealed up in the brown bottle, there's a good chance that beyond its expiration date, a lot of this decomposition will occur on its own anyway. Light just happens to make it so that it goes faster. But what they did was they took some hydrogen peroxide and they put it on this piece of cow liver. And what we can see is that the reaction to form that oxygen gas is very much apparent here by all of these bubbles. Now, why does the reaction occur so much faster on this piece of liver than it does if I just poured the hydrogen peroxide into a cup? Well, liver contains an enzyme called catalase. Now, enzymes are biological catalysts of sorts. Enzymes exist in your body to help your body break down materials faster and more efficiently than what they would have on their own. You've got enzymes all over your body. You've got enzymes in your mouth to help your food start to break down faster before it even gets to your stomach. And that's what enzymes do. Enzymes are catalysts, biological catalysts. And they work by helping the reaction to occur in a different way that is faster. And so that's what's happening here. The catalase inside of the liver is activating the hydrogen peroxide and causing the hydrogen peroxide to decompose faster than it would have on its own. And as a result, we get massive amounts of this oxygen gas forming on the surface of the liver because of this reaction. Now, the question that we will have to get into, and this is going to be the primary focus of our talk on Wednesday, but the thing that we're going to get into on Wednesday is the why. We've identified 4 different ways that we can increase reaction rates. What section 2 gets us into is an explanation for why these particular things and not other things increase the rate of reaction. Now, the general focus is over an idea known as collision theory. Collision theory is very simple. In order for a chemical reaction to occur, The reactant molecules that are in the reaction vessel have to run into each other. That's what happens when a chemical reaction takes place. The reactant molecules bump into each other, and as they bump into each other, bonds break, bonds form, and we get new substances. But it's not good enough that they simply encounter each other, that they simply bump into each other. When they bump into each other, they have to have two things. They have to bump into each other in the correct way so that the things that are reacting are close to each other. And they have to bump into each other with enough energy to actually cause the bonds to break that need to break. And when it comes down to it, there are only a small number of these collisions that actually occur and meet both of these criteria. What we'll talk about on Wednesday is how those four things that we discussed help to make these kinds of collisions more likely. And that'll explain why the reactions occur faster with those conditions than without them. So that's where we'll stop for today. Wednesday, we'll get into section 2, talking about collision theory and trying to explain things. And we'll get rolling out of there from there. Have a good afternoon.